Hello. We will continue our discussion of wave phenomena. And the first thing I'd like to talk about is reflection of waves. So the observation is that when waves hit an obstacle, or the end of their medium or boundary between media, then reflection typically occurs, which means that the wave reverses direction. A very good example is an echo from a distant cliff where you can hear yourself shouting with some time delay. Sometimes, if you watch carefully at the beach, you can even see a seaward wave after a big wave crashed on the coast. So here's how wave reflection happens in the one-dimensional case. So again, we consider the taut string. And it is fixed at this end, and some wave is moving in, and it's hitting this end, and it has nowhere to go. And what happens is it wiggles around here, and then it reflects with an inverted shape, meaning if the pulse was positive before, it becomes negative afterwards, and vice versa, if it was negative before, it becomes positive afterwards. Also, if we just have a loosely hanging rope, then what happens is that the wave is reflected. But in this case, the shape of the wave is not inverted. So it comes, if it was going up before, it is also going up afterwards. But in both cases, whether you fix the end or you have a loose end, some reflected wave is observed. A more complicated case is if a wave moves from one medium into a different medium. For example, again with our example with the rope, we can have a thinner rope and a thicker rope. So this one has more linear mass density than this one, and therefore the wave speeds are different in this light section compared to that heavy section. And in that case, what will happen is that part of the wave is transmitted further into the heavy section, and part of the wave is reflected backwards. And of course, since at the boundary, this point here where the two sections attach, the frequency of both waves has to be the same. The frequency of the wave doesn't change. It is just that the wavelength, if you have a sinusoidal wave, in the transmitted pulse will be different than in the incoming pulse. So the wavelength changes because the product out of wavelength and frequency must be the same, and the frequency does not change. If we have a two-dimensional or three-dimensional wave, then we can define wavefronts. And wavefronts are basically all the points that form the crest or the trough of a wave, or in general, all the points that have the same phase. You can connect those with lines or planes, depending on the dimensionality of the problem. And that is used as a representation of the wave. Moreover, we can define lines that go perpendicular to those wavefronts, and those are called rays. And that will be important once we cover optics in the later chapters of the book. So we observe that if we have a point source somewhere close, then those wavefronts are curved, and the rays go outwards like this. However, if the source is very distant, then this curvature is very small, and they look like parallel lines. And that is called, those waves are called plane waves, because in 3 dimensions, those are actually planes and not lines. So in that case, the rays will also go parallel and are no longer outward or inward going. So how does a higher dimensional wave, 2D or 3D, reflect? So again, it can hit some obstacle, which I've shown here. And we can now define an incident angle And the way we define an incident angle is we look at the ray of the incoming wave and measure the angle that it makes with respect to the normal direction of the obstacle. Normal direction means the direction that is perpendicular to this obstacle. So this is called the incident angle, or the incoming angle. And we can then also define a reflected angle, and that is for the outgoing wave, the angle that the ray makes with the same normal direction. And there's a very simple law for reflections of plane waves, that the angle of reflection must equal the angle of incidence. So those two angles must be exactly the same. Another case is the penetration into a boundary with different wave velocity, just like we had with the rope. Let's say we have a different velocity of the waves in this region compared to that region. And the wave fronts are coming in at some angle like this. Again, we can define the incident angle, theta I. And in this medium, the way it's pictured, actually, they slow down. And therefore, the wave changes direction. The transmitted wave changes direction. And there's a law for refraction also. This process is called refraction, just like there was a law for reflection. And the law of refraction is that the ratio of the sine of the incident angle over the sine of the refracted angle must be equal to the ratio of the velocity in this medium compared to that medium. And we will hear more about this law of refraction in chapter 32 when we cover optics. And waves can do a third thing when they encounter obstacle. When you put an obstacle in a multidimensional wave like this, so the waves are coming in this way, you observe that the waves seem to sort of flow around the obstacles. So if you just think of waves as the rays, then this is hard to understand, because you would think, okay, it just travels like this, and we can define a shadow region behind that obstacle. When you look at rays, you would think that it does never go into the shadow region. But real waves, actually, they bend around a little bit. And so, sometimes if you look far behind the object, the wave fronts actually reform as if nothing has happened. So that is called diffraction. And how much the wave can penetrate into this shadow region, that is flow around the obstacle, that depends on the wavelength. And as it happens, you can sort of roughly estimate how far that is by defining some bending angle, how much the ray actually has to bend around the object. And that should be given by about the size of the wavelength divided by the size of the object. So again, we will hear more about that in later chapters in the book. So let me now come back to a point that we discussed at the very beginning, that there's a difference between the wave speed and the speed of the particles. So if we consider the rope example again, and a sinusoidal wave given by this expression, then we know the wave speed is given by the ratio of omega over k. But the rope particles' velocities are given by a very different expression. And for ease of discussion, let's just consider one particular point x0. Pick any point, but keep it fixed. Then if we look at this formula, we can rewrite it just like this by putting the kx and the phi into parentheses. And that basically just looks like a fixed angle in the simple harmonic motion. So we have basically simple harmonic motion with some constant in here, which is the phase of the simple harmonic motion. And we know then what the velocity is. That's the simple time derivative. So the sine becomes a cosine, and we pick up an extra factor of omega outside. Or we can determine the acceleration by doing two time derivatives. If it derive this again, then another omega appears, and the cosine becomes a minus sign. And we can then express the factor of the omega square as k squared times the wave velocity square. So we get then, we sort of summarize this, we get then as the particle velocity the expression a times omega times cosine kx plus omega t plus phi, and I drop the 0 in the x because now I'm again considering any point. Since I can repeat this exercise for every such point x0, it holds actually for all points. And symbolically, we write that this is the partial derivative of this function with respect to time. And we denote it with those symbols. So the meaning of this symbol is simply the same as the usual derivative, but we at one moment, we only consider one particular position x, or x is held constant while we are performing the time derivative. And then similarly, the second partial time derivative is the particle acceleration, which has a omega square with the minus sign times the sine of kx plus omega t plus phi. And if we pick a wave that goes in the opposite direction, this one travels actually to the left. If you pick one that travels to the right, then we get very similar expressions. Only the omega then the omega term changes sign. So here we get an extra sign. So of course we could do a similar trick, looking instead of at the time, we look at the position. So now we focus on one instant in time and keep that constant, and then look at a pulse frozen in time, for example, this pulse here. And if we take the derivative of that pulse with respect to the position, then that is something like the slope, how much this pulse slopes. For example, here we have a positive slope, and here we have a negative slope. And somewhere over there we would have no slope at all. And the second derivative is the change of the slope, and that is something like how much does the rope bend. So here, for example, it doesn't bend at all. Here it bends a little bit, going from this direction to that direction. Up here at the top it bends a lot because it goes from upward to downward. And this curvature is important because it is actually defining how much force acts in the transverse direction on that pulse. So transverse direction always means this direction. So the more curvature you have, the more force. For example, here where we have a lot of curvature, we have the tension force going this way at this point, and this way at that point. And so if we combine those two forces, we get a large downward pointing transverse force. If we have no curvature like here, those two forces cancel each other out. There is no transverse force at all. And if we have just a little bit of curvature like here, where the curvature, the rope bends the other way, and therefore the resulting force is pointing upwards, but is smaller than in this case. So in general, the curvature is proportional to the force, or in other words, the transverse force is the tension force times the curvature. So we can then get similar expressions for the slope and for the force that we did for the velocity and acceleration of rope particles, only that this time we look at x rather than t. So we get very similar looking expressions there. And again, we make this funny symbol that we have a partial derivative with respect to space. And what it means is that while we perform this derivative, we only look at one instant in time. And for sinusoidal waves, at least, those two formulas, the one for the time and the one for the space, they look very similar. They just have different prefactors. So before we had an omega square here, and now we have a k square here. And this formula here is again for the right traveling wave. So we can put this together with Newton's law, which tells us that the mass times acceleration equals force. In this case, mass density times the rope particles transverse acceleration equals the transverse force, which is the tension force times the curvature. And formally, we write it like this, which is the wave equation. And this equation is valid actually for sine waves, since we know that this velocity which appears in here, which is the ratio of the tension force divided by the mass density, can be also replaced in the case of sinusoidal waves by the ratio of the omega, the angular frequency over the wave number. And so this wave equation is fulfilled by sinusoidal waves, and as it turns out, it is fulfilled by any general pulse that you assume, any general wave equation. So what you should remember from this discussion here, the expression for the particle velocity and acceleration, and the fact that the wave equation is nothing else but Newton's second law, that mass density times particle acceleration equals force. We come now to another characteristics of waves that obey such an equation, and that is the principle of superposition. We can ask ourselves what happens if we have multiple waves that pass through the same region of space at the same time. And that is called the principle of superposition. What it means is that we can simply add the deflections of each of the two waves, just like a normal addition of displacements. This is strictly true only for linear media, and linear media are those that result in a wave equation like the one I just showed you. What it basically means is that the wave speed is independent of things like the amplitude of the wave. In such a case, the sum of a wave function, of several wave functions, is always a wave function also. So you can form the combined wave function by a simple addition of the separate wave functions. And in particular, a multiple of a wave function is also a wave function. So let me now make this a bit more concrete by looking at a demonstration program. Let's assume that we have two pulses that travel from the, let me make this bigger. That we have two pulses that travel from the left and from the right of the screen against each other. So we will still see the component, the blue and the red, but now they actually merge and they form a bigger pulse in the center. And since they're drifting apart after that, they penetrate each other as if nothing has happened. And that is another feature of linear waves, is that waves can superimpose, and after that they no longer occupy the same region in space. they are not changed in their nature. So there's a third interesting case, and that is what happens if one pulse goes up and the other one goes down. Let's look at that. So the blue pulse stays the same, but the red pulse is now actually inverted. And what happens in that case once they hit each other? What happens in that case is they start to cancel each other. When they're just at the right position, then they actually cancel each other out completely. And this is called destructive interference. The other case is called constructive interference. Constructive interference leads to a larger pulse. Destructive interference leads to no pulse at all. So these are pulses, but let's now look at actual sinusoidal waves. And first we consider them going in the same direction. And what you are seeing here is only a blue wave because the red is hiding underneath. The green is actually the sum of those two. If we now introduce a phase difference between those two waves, the blue and the red, now you can actually see both of them. And there's still sort of constructive interference because the sum of those two is bigger than either one of them. But as I'm increasing the phase difference between them, the resulting pulses get smaller and smaller until they cancel each other out completely, like this. So this is very weird. We have two waves in a medium, but the resultant is no motion at all. Let's go back to that point. We have a particular superposition which is called interference, and there are sort of several cases for that. We either have cases where the pulses tend to cancel and we get destructive interference, or where they combine and we get constructive interference. Also, if the phases between them is any other arbitrary amount between exact cancellation or perfect addition, then we get partially destructive interference. And also, after the pulses are, no longer occupy the same region of space, they are undistorted and they continue their travel just as they did before. What this superposition principle makes possible is we can actually make other kind of waveforms as sine waves out of sine waves. For example, if I have one sine wave that looks like that, and a second one that looks like that, and a third one that looks like that, and they all add together, then we get a weird shaped pulse that looks like that, and it's almost like a sawtooth. Or different kind of waves like these, they can combine to make something that looks similar to a square pulse. Or one can look at it the other way and start with a square pulse and ask oneself what kind of sinusoidal waves does it require to make up those. And so for that, I have another program. This kind of idea is called Fourier Analysis or Fourier Synthesis. We can start with a step function and ask oneself, how can I get such a step function out of sinusoidal waves? And I start with the first sinusoidal wave, and it just looks like a straight line. And once I add the second one, it doesn't look like a square pulse at all yet. third one doesn't help. But the fourth one, the sum of those pulses is actually the gray line. And it starts to look a little bit more similar than the square pulse. And if I keep adding components, let me, for ease of viewing, no longer show the individual components, then it looks more and more like a square pulse. However, no matter how many components I add, there will always remain some little features that are a little bit of, it looks almost like noise that is sitting on top of those squarish-shaped pulse. Also, we can look at other pulse shapes. For example, here is a sawtooth. And this will have different components, the components for the sawtooth, than we had for the square pulse. And as previously, if I have fewer components, then the deviation between the desired shape which is just a straight sawtooth, and the actual shape that I sort of produced with this method is larger than if I have many components. Or we can look at a third shape, which in this case consists out of parabola that are connected. And that is easier for the sine waves to reproduce. So even with just 6 components, you can reproduce these parabola fairly well. So let's come back to the interference of waves. As I said before, that we have 3 cases: the constructive, the destructive, and the partially destructive, where the constructive interference happens if there is no phase shift between the 2 individual waves. And the destructive happens if there's a phase shift of 180 degrees. And the partially destructive is if there's any phase shift in between those 2 cases. And it's not just no phase shift and 180 degrees, but it can also be 360 degrees, or for the constructive interference, or 270 degrees for the destructive interference. So after all these technical details, I want to show you a different type of interference. And this is the interference that happens when a wave interferes with its own reflection. And you might remember that I did this little demonstration of waves at the beginning of the lecture. But now I'm going to do it differently. So what happens when the conditions are just right with, in the case of reflection of a wave, is you can excite a resonance in the system of the taut rope. And I'm going to try and do that just now. And you see that there is sort of a standing wave is forming, one that has, where there's just a fixed vibration pattern that doesn't seem to move in space. But it's not just one resonance frequency like we have seen when we discussed resonances. This system has many resonance frequencies, and it has different types of vibrational modes. So in this case, you see that the center of the rope is actually not moving much. And again, for comparison, this is the other kind of mode, where you have maximum movements in the middle and just no movements at the end. We have, for such standing waves, for those vibrational modes, we have nodes at the end, because that is where the rope is fixed. So it can't move at the post over there. Therefore, we must have the vibrational mode must be in such a way that there's no movement here and here. And then in between those two, we see large amplitude motions, which are called antinodes, and additional nodes, which are again places where the string doesn't appear to move at all. And we can characterize the vibrational mode, or the standing wave, by how many nodes and antinodes there are. And there's a sort of rule that each antinode is followed by a node, and each node is followed by an antinode. And of course, there's always a node at the end. And by the way, such modes exist also for music instruments. So here's a ukulele, for example, and let me try and excite the fundamental. It's a bit hard to see. So you see the same kind of pattern that at the end of, let me zoom out a little bit. Oh, it doesn't zoom out further. Near the ends of the string, there is very little motion, and in the middle there's a lot of motion. In the case of such a music instrument, the other resonant modes are suppressed. And so they are kind of hard to excite. I probably won't be able to do it. I don't know how well you can see it, but there tends to be, at roughly this place here, there tends to be a node, which before wasn't there when I plug it like this. So for those standing waves, we have several patterns or modes of vibration. And the pattern can be characterized by how many nodes and antinodes are in that pattern. And each of those patterns, each of those modes has its own characteristic natural or resonant frequency. And the lowest frequency mode is called the fundamental mode, and the frequency of it is called the fundamental frequency. And the others are called overtones. And the fundamental is the first, is also called the first harmonic, and the overtones are called the second, third, fourth, and so on harmonics. So how can we actually know what kind of frequencies those resonant frequencies are? Well, the standing wave, it has to fit within the system, meaning that it must produce a node at those two ends, because those ends are fixed and they can't move. And therefore, the fundamental, or the first harmonic, is one, that's the simplest one. That is one where the wavelength, the usual sinusoidal wave, goes like this, and you can sort of can think of it continuing beyond the boundary there. So if I duplicate this picture here, and I just show it at one instant, so we have a node here, and we have a node here, and we have an antinode in the middle, and we can sort of imagine the wave continuing like this. Of course, none of that is physical because there's no rope here. But then the distance from here to here would be the wavelength lambda. And therefore, the distance from here to here is half a wavelength. So in general, the distance from one node to the next node is 1/2 of the wavelength. And the distance from a node to an antinode is 1/4 of a wavelength. And since the ends are fixed, therefore there are at least two nodes. So the fundamental wavelength is given by that the length equals exactly 1/2 of the wavelength, or the lambda 1, the fundamental wavelength, must be equal to twice the length. So if we now go to a higher order mode or to an overtone, then we pick up an additional node in the middle. So now we have two antinodes, and one node in the middle, and one node at the beginning, and one node at the end. So in this case, lambda 2 is equal to the length. So now the wavelength fits exactly inside the two boundaries, inside the length of the rope. So lambda 2 equals length, and or we can also say lambda 2 equals twice the length divided by 2. So it's kind of like the fundamental wavelength divided by the number 2. We can then move to the next overtone, where we have two nodes in the middle, two at the end, so 4 altogether, and 3 antinodes in between. And we get that the wavelength is 2/3 of the length. And therefore, we have lambda 3 equals twice the length divided by 3. Or in general, we have that the wavelength of the nth mode is twice the length of the rope divided by some number n. If we invert this with, if we use the equation frequency times lambda equals velocity, then we can get the frequencies that are associated with those wavelengths. And we find that the overtones are integral multiples of the fundamental frequency, and the fundamental frequency is given by the velocity over twice the length. Thank you.